going along in our little adventure through a quick version of quantum mechanics, right? So remember, the idea is that I'm going through one section in Thomson, right, where he's reviewing like a bunch of quantum mechanics concepts, but I'm also like integrating the modern physics quantum mechanics, 2 to 3 chapters interspersed into it in order for us to get a much better coverage of everything. Okay. Is this where we start? Yeah. So last time, right, we had this idea called the wave function, the psi thing, right, over here on the side here. And this thing kind of describes everything about a system, a particle, whatever you want to call it, right? And whenever you want to measure something on that particular system, so this is a lowercase psi, right? Whenever you want to measure something about that system, you have some sort of operator on it, right? And there's some quantum mechanics operator, and then you act on it with the total system psi, which is usually a capital psi, okay? And this can depend on space and time, right? And whatever eigenvalue comes out, right, of that, it will project that state to an eigenvector, right? And this is the actual value you would actually measure. So if A is like the energy operator, right, lowercase a will be the amount of energy in that system. If the operator A is a momentum, right, the lowercase a will actually be the momentum of that particular system or particle, right? So this is the eigenvalue. If I can spell eigen. Ooh. It's just a little difficult on top of the screen here, right? That's actually what you measure, and then the eigenvector is the state will actually get projected out into that particular state, or the wave function collapses into an eigenvector of that particular operator. Okay, and in general, these psi vectors are very complicated, and we'll go do a little drawing of this. Okay, but the idea is that you want to simplify things just in all physics. Yeah, David? The wave function changes. So that's a very good. So the question is, what do I mean when we say the wave function collapses? So this is one of the, if you search on YouTube, there's a bunch of arguments about what does it mean? Is this really true, right? This is a way for us to do the mathematics in order for the predictions to come out correct. If that's that's probably not satisfactory, because right, you would think that, well, if my, let's say I have a bunch of molecules floating in this room, right? And I measure the amount of energy in these molecules, right? You would think that, well, by measuring it, it shouldn't affect, I mean, if I have a very good device, right, then it shouldn't affect those molecules, right? But what happens quantum mechanically is that when you measure things, you actually changes the state. And this is actually, kind of physically true. You can't really measure something without actually changing it, right? And in the derivation in quantum mechanics, what happens is that what happens is that it basically sets that one particular, one way to think about it is that, so when I have a bunch of molecules floating around this room, right, I'm not sure what their energy is, right? But once I measure it, right, at least at that instant, I know exactly what the energy is, right? Just for an instant, but then they go off and evolve, right? So that's kind of what conceptually is trying to do, this mathematics of projecting your system to an eigenvector of that with a particular eigenvalue of that particular operator. That's what it's trying to describe. Okay, it may not be, and I think there are other interpretations, right, of quantum mechanics that may try to do, like, I think they're like multiverse interpretation and stuff like that, where every possible thing actually really happened. But let's just stick with the Copenhagen, and then we'll just do the math on it. Okay. So that's a really good question, though. Okay. Okay. So the psi functions, right, are usually pretty complicated. But what we can do using our math methods, or you usually do this in like Calc 3, Calc 2, or something like that, right? When you do a Fourier series of some periodic functions, you can actually figure out, you can actually make any functions out of sines and cosine functions. And that's what the example down here is trying to show you. So if you have a square wave, right? Let's say you have, this is the box. Go away. Okay, so I think it's trying to click on the Wolfram alpha here. Let's say you have this, square function, right? It's not a sine and cosine function, but if you add up enough sines and cosine function, it'll emulate that. So for example, the first order approximation is this red one, which is not very square, right? But as you add more and more terms in this Fourier series, it gets closer and closer to it. And where I think the blue one is probably the closest one, right? You can also approximate a straight line using sines and cosine functions, right? Triangular waves, semicircles even. Okay. But these wave functions follows, some rules, right? Well, first of all, it has to be a function, right? Where, for each independent variable, there's always one dependent variables, right? So for example, right, this will be a function, right? XY, right? But I think that's not a function. Let me see if this is not a function, right? Where if for each X, you can have two possible values, that doesn't make any sense, right? In a physical system. Okay. It also has to be piecewise continuous. What does that mean? Piecewise continuous mean that, let's say you have, a barrier, right? A finite barrier where, there's some amplitude for it to go in, right? Some oscillation, right? And then it'll kind of decay exponentially in this barrier. And then it'll kind of go on and do its own oscillation afterward. What's happening here is that the probabilities for it to be from one side to another side of a barrier has to be continuous, because it doesn't make sense for you to have a very high probability here and nothing here, right at a barrier where you have an infinitesimal change in position, but then the probability just cut, is not continuous. So that's what it means by piecewise continuous. Okay. And also have to be integratable to some finite values. So for example, if you had, let's say your wave function is like x squared or something like that. So x squared is actually integrates to infinity from negative infinity to positive infinity, right? So you cannot integrate it. The integral cannot go to infinity, because then you just have infinity as a probability. That doesn't make any sense, right? Another one that integrates to a finite number, like maybe an exponential decay, right? Or Gaussian, right? These all integrates to finite numbers when you go from minus infinity to positive infinity, right? It has a definite probability you can calculate, right? Or infinities is like, how are we going to calculate that? If you ever get a little bit more into the thing that is from which the standard models derive from, which is called the quantum field theory, you do run into infinities, and then we do these things called renormalization to get rid of the infinities, and then Dr. Miller can comment more on that. It doesn't have to be positive. It actually doesn't even need to be a real number. It could be a complex value. It's just so it just has to integrate to some finite value. Okay. It can't be negative infinity either. That's the thing, right? Okay. So this wave, the whole wave function, right, can be determined, right? We're going to break them up into little pieces, right? Where the original wave function is this capital psi. Each of these lowercase psi represents one particular k, right? Remember in a natural unit, this wave number is actually the momentum without having to do any conversion between wave numbers and momentum, right? So each of these waves will have different momentum. Once you have the momentum and the mass of that particular particle, you also know its energy. So this is, if you know what the P is, then you basically can figure out what the wave is going to look like. But then you also have to figure out what this normalization thing is, right? Okay. So how do we use the Schrodinger equation to predict, for example, where is this particular particle is moving around? Where is it going? Okay. So now we're going to go back to Survey, Modern Physics book again, where it defines that, well, this probability, well, Unfortunately, Survey does a slightly different nomenclature compared to mine. So I'm just going to scribble over it. So this is this row here. This row, dx, if you integrate this over all of space and time, all of space, sorry, not all time, right? So this is a spatial integral. You will actually find the probability of finding that particular particle in some space, okay? Okay. What's inside here, right, is this row is actually the psi square, which is exactly how Thomson also describes it. So this equation is from Thomson, okay? Where this equation is from Survey, okay? That's why I scribble the row over the P, okay? And so to calculate this, to figure out what's inside this integral, you have to calculate psi star psi, okay? So the square of the wave function kind of tells you, how kind of like the what's called the probability density, right? So if you integrate that density, then you figure out what the probability is. Okay. Yes,
Professor Tu, so there was a question in the chat actually a minute ago, and actually, Cliff, maybe you can clarify. Were you talking about the wave function being positive, or because that might be important?
I was referring to a homework question where it had a graph and it was asking about the Born interpretation. And one of the graphs had a wave function that was going both positive and negative. And I was thinking in terms of a particle in a box, and you can't really have a negative energy. So I wasn't sure if that was valid or not.
well, so remember, these wave functions are not describing the energy, right, necessarily, right? So so it is okay for the wave function to be negative, because maybe at different parts of it could be positive. And also the other thing is that you are going to be squaring these things anyway, right? So the probability always comes up positive, even if you have your wave function is negative. Okay.
All right.
The reason why that's important is that sometimes there could be constructive or destructive interference between two different processes, and you actually do want that destructive interference to occur. Okay.
Got it. Thank you.
That's a good question too. Okay. So going back to our little probability density thing, right? So let's just for now, assume that these particles don't decay, just, a stable particle running around, okay? So if we integrate over the density all of space and time, right, like what I just did up top, dx, well, this will be a triple integral in this case, but let's just simplify things by doing just in one dimension for now, okay? What's going to happen is that, right, if I take all the particles in this room or in your room, wherever you're zooming from, right, the number of particles is conserved, right? You're not going to have additional particles coming in, especially in an isolated system like that. Okay, so this is basically like the conservation of particles, right? So if you're just counting like nitrogen atoms or whatever you want to talk about, okay, what we're going to do is do like one step harder. Instead of integrating this volume of all of space, right? What we're going to do is integrate over some small volume, and this is what the book is trying to illustrate here with this little circle here, this little H-shaped circle in the book. Okay, there's some volume where we're trying to calculate the probability of a sets of particles being in that particular oval, this little egg shape. Okay. The way you figure that out is that, well, maybe these particles are moving around, okay? And we're going to figure out what this J actually really means, okay? So let's just think about that J as kind of like a current of water in the river or whatever you want to call it, okay? It's analogous to electric current and also water current in real life, okay? And what's happening is that if you're looking at this little volume, right? And we define a little area called ds, some differential piece of the volume, right? The amount of particles flowing out over this volume, right, should be equal to the change of number of particles inside that volume. Okay. All right. Let me do a more solid, an easier example. Okay. Let's say I have a little tube here, right? And inside here, there's like 1,000, particle of some sort, okay? Right? If this little pump here is pumping out 10 little particles per second out, right? 1 second later, you have 990. 1 second later is going to be 980. Sorry, 908. Yeah, 980. 970. So the number of particles inside there is going down, right? So this is, those of you who had still remembers your E&M, right? This is kind of like the flux, right? Coming out, okay? In fact, this flux is negative because you're losing particles, right? And inside here is kind of the total number of the density of the particle, right? Which is actually going down, okay? So to quantify this, right? If you take how fast, right? Time derivative, think about how fast things are happening, right? How fast is the density of the particles or is going down, right? Or if you integrate it over the volume, right, that's actually the number of particles inside there. So this is the 1,000 number that's going down to 990, 980, 970, right? Minus, because this is a flow outward, okay, times this weird J variable that we're going to call current, okay? How much current is flowing through this little surface, integrated over all the possible surface that it could flow out of, okay? In this example here, the simpler example, the current is actually just 10. Well, right? Okay. And then the change is -10, right? Because it's flowing out. Okay. So hopefully that gives you kind of a better intuition of what these variables are trying to describe. Okay. The density of the particle, right? How it changes with time is related to how much flows out of that surface. Okay. All right. Okay. And now we're going to do some fancier mathematics called the divergence theorem. You just have to look it up where it basically converts a surface integral to a volume integral. Okay. I'm not going to try to prove it because I don't actually remember how to prove it, but that's okay. But we can use it where we're replacing, instead of this dot product between the current and the surface, we're going to using the divergence theorem. This is actually the gradient. Okay. Dot product that with the current, and when you do that, it changes the surface integral to the volume integral. Okay, right. And now we have two things that are under volume integrals, right? This is just a volume integral. This is just a volume integral. Well, if those two are the same as each other, the stuff that we're integrating better be the same, right? So in this case, what we're going to bring down is that, well, this dt rho, right, the time derivative of the density is going to be equal to, let me just write it out, okay? Right, the left-hand side is partial by partial t of the density, right, which can depend on xn time, okay? Oops, too many parentheses, right? And then the right-hand side is just negative this gradient of the current, which is a vector also. But it's a dot product, so it turns it into a scalar. Okay. Right. And then if you move this to the left-hand side, that means that the grad J plus the density, the change in density, partial rho by partial T, right, has to add up to 0. Okay. All right. So how does it help us interpret what's going on with the Schrodinger equation? Remember? So let's do it the simplest example possible. Let's do a free particle. Okay. So remember the Schrodinger equation is that, well, the time derivative of psi, right, is equal to the Hamiltonian acted on the psi. There's probably a minus somewhere, right? Did I do that right? Where's the Schrodinger equation? Oh, there's an I in front here. Oops. That's what I get for trying to remember equations off the top of my head. Okay. Okay. So, and I think there's a minus between these two. Okay. What's happening is that, well, for a free particle, the Hamiltonian is just going to be p squared over 2m, right? You keep the minus sign here, okay? And p from last time, I think we remember that is some sort of spatial derivative, right? each P is kind of a spatial derivative, right? So the way we're going to write this is that this is going to be some second derivative with respect to space, right? Let's write the 1/2m in front, right? Acting on psi, okay? Okay, so this is the one-dimensional version. If you want to change this to the general three-dimensional version, so you're doing a second derivative in each of the directions, that's actually just the gradient square, okay? That's 1/2m, okay? And that's how they ended up with equation 2.21 over here in the book, okay? So steps that, you know, the book really skips. Okay, well, I mean, because we're interested in psi star psi, right? The complex conjugate, right, is pretty simple. Well, if we just kind of star everything, right? But whenever we see an explicit I, we have to negate it, right? So we just get a star on here, and then negate the I here, okay? If we try to multiply those two things together to figure out what this row thing is, right? Okay, so psi star psi, okay, let's see, it's going to be, well, there's a few algebra steps. That's just a lot of calculus stuff where you can actually factor out one of the gradient operators, okay, and find that the psi star rad of the regular psi without the star subtracted from this is going to be equal to exactly what's up here, okay? Because that's just kind of, it's actually like you're doing the reverse of the chain rule, okay? So if you actually act it on this, you're going to get grad square back, okay? And that's the reason why we're breaking this up like this, okay? Okay, all right. The reason is that, well, if we're comparing this J thing to equation 22.0, so 2.20, right? This thing in here, right? We have this grad dot thing up here. We have this grad dot thing down here. That means this current, right, thing, right, this J thing, let's not even call it a current yet, but it is analogous to that. It's going to be, right, this psi star, the gradient of the wave function minus the wave function itself with the gradient of its complex conjugate with some bunch of factors in front that you have to bring around, okay? So this 1/2im comes out, okay? Right, because the I actually has to come down here also, okay? All right, so what are we trying to say here, okay? So remember, you can do this with some arbitrary wave, right? Okay, with some momentum P, right? Once you know what the momentum is, then that defines that whole wave. And then if you have an arbitrary wave function, you can just add up a bunch of these plane waves. So these are actually called plane waves because they have one particular momentum, okay? So if we plug in equation 2.24 to here, okay, what you're gonna see is, I think we don't have to go through all the little calculus stuff, right? Once you plug this in, so I'm basically plugging in psi star psi into here, and then I do the complex conjugates of it, right? Which is, oops, n. This could be complex also. Instead of plus I, right, I have minus I p dot x minus e times, right? I plug, you know, brute force, plug it in, and then I take the gradient of it, okay? Okay, I'm only going to do this in one dimension, just in the x direction, right? I'm only doing the partial x direction, just to show you guys how this works, okay? If you plug that in, you end up with this, you know, equation with two n's, right? The reason you end up with two n's because each of these is psi star psi, right? So you should end up with two n's, okay? Okay. In fact, you probably should put the star here just in case they are complex, okay? Did I do that right? No, I put the star in the wrong place. Star should be up here. Okay. Okay, but the thing is that, right, this gradient in one dimension is just a spatial derivative, okay? if I do the spatial derivative of this against this wave function, what's going to happen is that you pop down an I times P. See where that comes down, right? Because you're only doing derivative with respect to X, right? Okay. And then the derivative of e to the ax is a times e to the ax, right? Okay. Similarly, you have a minus ip coming down here, okay? Okay. And the neat thing is that when you multiply all these things together, okay, you get the n, you put the n's together, right? I lost track of which one has the star, which one doesn't, but it doesn't matter. Okay. Right. What you can do, since the IP is common in front of both terms, you can factor that out, right? In fact, you get two of them because these are the same terms, so you get 2 times IP that, right? That's what factors out, right? And then this 2i cancel out with the other 2 i's, okay? And then you have this wave function at the end here, okay? Okay, and this thing is just the same thing as the, so you have P over M, and then you have n star n, which is just the magnitude of n squared, okay? And then you have the wave function e to the minus IPX times, I'm just gonna write this out just so you guys can see it, right? I'm gonna write out the first one at least. IPX minus ET, right? What does that multiply to? And there's a second term like that. What does this multiply to? 1, right? So because this is just e to the 0, right? Anything to the power 0 is just 1. Okay, so that was a lot of, you know, little fun exponential calculus stuff, right? But what ends up happening is that this j, right, is just n squared times momentum, which is kind of fun, right? Divided by the mass. Momentum divided by mass in classical mechanics, that's just the speed or the velocity of that particle, right? Remember that momentum is mass times velocity, right? And therefore velocity is just momentum divided by mass, right? Okay. This n squared thing here, right? This requires a little bit of physical intuition. Remember going back up to here, all the way up here, where we're drawing this thing, right? Okay. This current thing, okay, now we have to actually go to the river or the electrons flowing around analogy, right? This is describing how much particle is flowing in and out of your surface, okay? Okay, so where big N is just a normalization in front of your wave function, right? What you're trying to describe here is how many particle is flowing in and out of your surface with some velocity v, right? And the number of particles is this lowercase n, right? Where this is actually the number density of the particles, okay? So big N is related to the wave function, where little n, which is actually n squared, right? That's the number density, okay? Because that's what physically is flowing, that's what that J is actually trying to describe, right? The particles flowing in and out of your surface. Unfortunately, those of you on Zoom don't see my all weird hand wave functions, but okay. Okay. So putting all this together, right? So this wave function, so this current, right? Now we can kind of think of it as a current, right? It's going to be can be calculated by, right, taking the psi star grad psi minus psi and times grad of psi star, okay? And that turns it into basically for a free particle, meaning there's no potential, there's no potential term, okay? That's just going to be the momentum, okay, for a free particle, okay? And this current is really describing how the density of particle flowing in and out, flowing around, okay, in your system with some velocity v, okay? Okay. So the important thing to know is that this current is actually telling us the density of particle flowing from one to maybe from one volume to another, okay? And this is going to be important when we're trying to calculate this thing called the transition amplitude, where we're trying to figure out, well, if you have some particle coming in with some momentum P1, let's do the 4 momentum. I can erase that little arrow on top, right? Okay. What is the probability, right, with the question mark, for it to change to have momentum P2, right? That's sort of what we're trying to figure out, okay? And this J, right, is going to be related to that, okay? Right? And this flow is proportional to n squared. So therefore, right, since J is going to be related to this probability, the normalization square, right, is going to be proportional to J, therefore it's proportional to the probability of the thing transferring, of changing momentum from one to the other. Okay, so we're kind of diving like kind of deep into this, but hopefully once we get to the end of the chapter, we'll see that, sorry, end of the section, right? In Thomson, this is just one section. We're going to see why, right? Calculating size, basically these n square, the capital N square, right? That's the important thing we're going to be calculating, and that this is going to turn into these matrices we have to calculate, okay, when we do the relativistic version of it. Okay, any questions? I know that was kind of a deep dive into things, one thing related to another thing, related to another thing, and hopefully it'll allow us to calculate the probabilities at some point. Any questions? I'm just taking a sip of tea to refresh. Okay, so now we kind of thought about, did a lot of mathematics with the wave function stuff, right? And for whatever reason, Thomson is going to jump to the operator side instead. Okay, now we're the next subsection, we're going to think about the operator stuff instead. I think it does make sense for him to jump back and forth between the two, because you kind of have to describe both, you know, because you have, in quantum mechanics, you have this wave function thing, you have the operator thing, and it's the action between them that determines what's going to happen as a function of time. Okay. So what we're going to say is that, well, let's say we have some state, okay, let's just look at it down here, where we initialize it, okay, it has some initial energy, okay, EI, okay, so therefore, right, it'll be in some eigenstate, psi I, okay, I for initial, okay, where it is the eigenvalue, eigenvector of, since it's energy we're measuring, this is going to be associated with this Hamiltonian, okay? So the Hamiltonian is basically the total energy of the system, okay? Right? And so according to Schrodinger equation, right, this wave function is going to evolve as a function of time. It's going to change as a function of time, right? Following the Schrodinger equation, where I just kind of intersect it in here, right? Usually is, this is the first step and this is the second step, right? Where the H operator, the Hamiltonian operator, since it is in, since the state is in this eigenvalue, eigenstate initially, right, will give you EI as the eigenvalue, okay? Let's say initially the state has 10 MeV energy, right? When you act on it with the Hamiltonian, it will give you 10 MeV as the eigenvalue, okay? Okay. Right? So since this is just a partial by partial t, you know, let's say, you know, some function equal to some constant times that function, let's call that, right? We can call that EI, right? Times some function, right? If you integrate both sides, then you end up with, wait, what do you do with this? You do a separation of variable, right? So you do a little separation of variable, then you find that the solution is just going to be e to the negative I, well, there's negative I in front, EI, right? Something that's exponential, right? When you have a first order time derivative the solution is always this exponential function. Yes. Should we do an explicit example of that? Ivan's nodding. Okay.
Yes.
Yeah. Okay. Let's just do a differential. If I can remember one. I think usually like maybe like so let's say you have some function f, right, that depends on time, right? And let's say it's an exponential decay, so there'll be a negative here, right? And this will be maybe some time constant tau, okay, times that same function. So where this is just a function of time, okay? Okay. So if you want to do the so this is a constant, right? The way we solve this, if I remember right, is then you separate the stuff that depends on f on the left-hand side and the stuff that doesn't depend on f on the right-hand side, okay, which is going to be dt, if I did that right, okay? So now, right, I have, something that depends on f on the left-hand side, something that depends on t on the right-hand side. I'm going to integrate both sides, right, from maybe t equal to 0 to t equal to some capital T or something like that, right? So the integral of this, right, you can factor out this 1 over tau. The integral of 1 over a function, right, that's just the natural log of that function, right? And this is just a constant integral, so this will just be evaluated at t minus t, well, t evaluated from little t equal to capital T, or this is not the period, it's just some time that I'm defining later, okay? Okay, and so 1 over tau, natural log of f equals to time, and then natural log of f equals to that time, oops, not tau, that one goes in the numerator, right, over tau. Right, to solve this equation for f, you just exponentiate both sides. So this is e to the minus t over tau, right? So whenever you have a time derivative, the solution is always going to be this e to the some exponential either growth or decay, right? Depending if the sign in front here is positive or negative. Is that okay? Hopefully that's correct. Dr. Miller can check me because I haven't done one of those explicitly for a long time. Multiplying tau. Oh, you're right. Did I move that to the wrong place? Yeah, multiplying tau. That's right. So typically the reason I thought it was dividing tau is because tau is usually represent the time constant, of a decay or something like that. But yeah. So I should have defined tau as 1 over in the first place, but okay. But the main thing is that it's some exponential, right? When you have a first order derivative, then you have exponential as the solution. Okay. So the solution of this, you can even check it. You plug this back in here, right? It's going to be some exponential piece here, right? Right, that's the time dependent part, okay? And we didn't take care of the spatial dependent part yet, so there could be yet another funky function, okay, that depends on space, right? This piece depends on space, this place depends on time, okay? And the piece we're gonna call that depends on space is we're gonna call it phi instead. Just so there's more Greek letters running around, okay? Okay, right? So this is the initial wave function, right? That depends on space and time. This is the spatial piece. This is the temporal piece. Okay, the temporal piece is always going to be e to the negative I ei t. Okay, this is going to actually, you can just think about that as kind of an oscillation because it's an from Euler's equation, right? This is just a combination of sines and cosines, right? All right. Okay. So there's this spatial piece that we still have to take care of. Okay. So let's say if we want to find the expectation value. So let's figure out what that is first. Okay. So if I was to make a measurement of something, okay. Okay. If I was to make a measurement of something using some operator A, right? As I stated before, right? You act on it on the wave function, okay? But in order to calculate in order to figure out the value on average you're going to get, okay, which is known as the expectation value, you also have the psi star on the other side. In fact, you actually have to do this thing is a psi star. Okay. 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 So this is where I'm not sure if Thomson did this on purpose, but this is where Thomson jumped into this known as the Dirac bracket notation, where instead of writing it like this, he shorthanded by writing it like this. Okay. And it does make sense, hopefully. So some of you guys might have seen this in the other classes where, oh, if you have, a bunch of numbers, right? If I want to kind of take the average of that, right, you put a little alligator clip around both sides. Another symbol for that is kind of like, let's say, X average or something like that. Okay. So think about this operation here as kind of like figuring out what the average value you would get out of that operator if you were to measure it on that particular system. Okay. Okay. So to do that, so this is where the bracket notation actually kind of bites me, right? The way you represent this side of the this right-handed psi function, just think about it as kind of like psi star. Okay. It's technically not, because these will turn into vectors eventually, so you actually need psi dagger. But in this one dimension, in this simple case where we're dealing with scalars as a wave function, let's just think about that as psi star. The thing on the right here is just psi. Okay. So essentially what he's writing is psi star A operator psi. Okay. Okay. Right. And then with this, since you're averaging over all space and time, you're actually integrating this over all space and time, which is going to be the symbol D3X. Okay. Where X means XYZ. So you're integrating all of volume of space. Okay. And this is what this shown here. Okay, he does do the dagger. Okay. Okay, so he is keeping it general. Okay. But for now in a classical non-relativistic quantum mechanics, just think about it as just a complex conjugate. Okay. Right. Okay. And remember this dagger thing? I think I talked about this with the matrices, right? It just means the complex conjugate and transpose. And this is just to make the linear algebra work, because otherwise you're taking like a row vector, a column vector with a column vector, which doesn't make sense. Okay. All right. So how are we doing this? Okay. So in the example, I'm going to take an example from Survey. Okay. We're going to use this as just with the scalar version, right? Remember this psi star psi, right? Okay. Right. Right. That's the same thing as taking the square of the wave function, because in general, it's a complex number. Okay. The expectation number, let's say in the position X, right? It's just this integral thing, right? Where you multiply by the position X to psi star psi, okay? And then you have to integrate all of space, okay? In this case, since we're doing the one-dimensional version, that's just integrating all along the x-axis, okay? Okay. But if we want to figure out how the expectation value of this observable changes, right? Well, maybe we want to take the time derivative of that particular observable, okay? Whenever you see the A here, you can just replace it with X for now, because we're doing the X version of it, okay? So what happened is then, well, that means, right, we have to integrate psi star, so the time derivative of psi star times A, okay? Because there's the chain rule, the product rule, where, and then the time derivative with regular psi without the star, just replace this with star for now. Let's not even think about that, okay? So these are just the same operations on the different pieces of the complex conjugate of the wave function or not, right? And the thing is, it's also in different order, right? These are not in the same order. One, you did the operator on psi first. The other one, you did the operator on the derivative first, okay? And since this operator, if the operator is time independent, right? This partial derivative of the operator with respect to time should be 0. So therefore, you can actually set this whole equation equal to 0. Am I making sense? Okay. Okay. So using this Schrodinger equation again, I'm just trying to follow the book itself. Okay. Let's say this operator is the Hamiltonian. Okay. We're just replacing this with the Hamiltonian. Okay. So we plug in the Hamiltonian here, plug in the Hamiltonian here. Okay. Right. Sorry, that's wrong. How did I go from there to here? Because the Schrodinger equation is the partial by partial t xi of the wave function, right? The Hamiltonian times that wave function. Okay, let me think about this a little bit more because we're out of time anyway. So we'll start with this. I just want to make sure that this step where we're comparing the Hamiltonian to whatever this arbitrary operator we're talking about makes sense, okay? So I think I need to fill in a little bit more in here between these two steps anyway. Okay, sorry about that. So I was hoping to get to the end here, but that's okay. We'll start off with that on Wednesday, okay?